Learning goals. Welcome to this learning session on understanding and balancing chemical equations. In this course, we shall address Introduction to Chemical Equations and Word Equations, Balancing Equations, Conservation of Mass, Counting Atoms and Balancing Simple Equations, State Symbols and Balancing Complex Equations, Practice and Application. There will be a quiz at the end to test your knowledge. Introduction to Chemical Equations. Chemical equations serve as a concise, symbolic representation of the changes that occur during a chemical reaction. They provide chemists with a universal language to describe how atoms rearrange to form new substances. Understanding these equations is fundamental to predicting reaction outcomes and calculating quantities of reactants and products.
These equations are more than just formulas. They are powerful tools used across various scientific disciplines, from pharmaceutical development to environmental science. For instance, chemical engineers rely on balanced equations to optimize industrial processes, ensuring efficiency and minimizing waste in large-scale production. Reactants and products defined. In any chemical reaction, the substances initially present are known as reactants. These are the starting materials that undergo a chemical change, breaking existing bonds and forming new ones. Reactants are typically written on the left side of a chemical equation. Conversely, the new substances formed as a result of the chemical change are called products. These substances have different chemical properties from the reactants. Products are always written on the right side of a chemical equation, separated from the reactants by an arrow, which signifies yields or forms. Understanding word equations. Word equations provide a simple, descriptive way to represent chemical reactions using the full names of the substances involved. They are particularly useful for introducing chemical reactions without requiring knowledge of chemical formulas. For example, instead of using H2O, you would write water. When writing word equations, two or more reactants or products are separated by a plus sign plus. This sign indicates that the substances are combined or produced together. The arrow in the middle signifies the direction of the reaction, pointing from reactants to products, and is read as reacts to form, or yields.
Example of a word equation. Consider the reaction where iron oxide reacts with carbon to form iron and carbon monoxide. In a word equation, this is expressed as iron oxide plus carbon produces iron plus carbon monoxide. This clearly identifies all substances involved without complex chemical notation.
This specific reaction, the reduction of iron oxide by carbon, is crucial in industrial metallurgy, particularly in blast furnaces for producing iron from iron ore. The carbon acts as a reducing agent, removing oxygen from the iron oxide to yield metallic iron, a process vital for steel production worldwide. Balanced chemical equations are a more detailed and quantitative representation of chemical reactions, using chemical formulas instead of names. The fundamental principle behind balancing is the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. Therefore, the number of atoms for each element must be identical on both the reactant and product sides of the equation. To achieve this balance, coefficients, whole numbers, are placed in front of the chemical formulas. These coefficients indicate the number of molecules or formula units involved in the reaction. It is crucial to only change coefficients and never alter the subscripts within a chemical formula, as this would change the identity of the substance itself. Law of conservation of mass. The law of conservation of mass, first articulated by Antoine Lavoisier in the late 18th century, is a cornerstone of chemistry. It dictates that in a closed system, the mass of the reactants before a chemical reaction must equal the mass of the products after the reaction. This means atoms are merely rearranged, not lost or gained. This law is why balancing chemical equations is so critical. If an equation is not balanced, it implies that atoms are either appearing or disappearing, which contradicts this fundamental principle of nature. For example, if 10 grams of hydrogen react with 80 grams of oxygen, exactly 90 grams of water must be formed, demonstrating the conservation of mass.
Counting atoms in equations. To balance an equation, the first crucial step is to accurately count the number of atoms for each element, on both the reactant and product sides. This involves examining the subscripts within each chemical formula and multiplying by any coefficients present. For example, in 2H2O, there are 2 times 2 equals 4 hydrogen atoms, and 2 times 1 equals 2 oxygen atoms.
A systematic approach, often using a table, helps keep track of atom counts. List each element involved in the reaction, then tally its atoms on the left, reactants, and right, products. This clear comparison immediately highlights which elements are unbalanced and require adjustment through coefficients. Balancing simple equations, step by step. Let's balance the reaction of hydrogen gas with chlorine gas to form hydrogen chloride, H2 plus Cl2, HCl. First, count the atoms. On the left, there are 2H and 2Cl. On the right, there is 1H and 1Cl. Both hydrogen and chlorine are unbalanced. To balance, we need 2H and 2Cl on the product side. Placing a coefficient of 2 in front of HCl on the right side achieves this: H2 plus Cl2, 2HCl. Now, both sides have 2H and 2Cl atoms, satisfying the law of conservation of mass. This simple example illustrates the core process of adjusting coefficients. Example of a balanced equation. Consider the balanced chemical equation for the reaction between iron oxide and carbon, Fe2O3 plus 3C, 2Fe plus 3CO. This equation tells us that 1 unit of iron oxide reacts with 3 carbon atoms. The products are 2 iron atoms and 3 carbon monoxide molecules. Let's verify the atom count. Element Fe on left 2 on right 2. Element O on left 3 on right 3. Element C on left 3 on right 3. As shown, the number of atoms for each element is equal on both sides, confirming the equation is balanced. This ensures mass is conserved during the reaction. State symbols in chemical equations. State symbols are crucial additions to chemical equations, providing information about the physical state of each reactant and product under the reaction conditions. These symbols are written in parentheses immediately after the chemical formula. They help chemists understand the practical aspects of a reaction, such as whether a precipitate will form or if a gas will evolve. The 4 common state symbols are S for solid, indicating a substance in its solid phase; L for liquid, representing a substance in its liquid phase; for gas, denoting a substance in its gaseous phase; AQ for aqueous solution, meaning the substance is dissolved in water. These symbols are vital for accurately describing reaction conditions and predicting observable changes. Worked example, balancing complex equations. Let's balance the reaction of aluminum with hot dilute sulfuric acid, Al plus H2SO, Al2SO3 plus H2. We also need to include state symbols. First, write the unbalanced equation with known formulas and states. ALS plus H2AQ, Al2SO3AQ plus H2G. Now, balance the atoms systematically. Aluminum Al, 2 on right, so add 2 to Al on left, 2Al. Sulfate SO4, 3 on right, so add 3 to H2SO4 on left, 3H2SO4. Hydrogen H, now 3 by 2 will 6 on left, so add 3 to H2 on right, 3H2. The final balanced equation is 2ALS plus 3H2AQ, Al2HQ plus 3H2G. This systematic approach ensures all elements are balanced. Practice and application. Mastering the art of balancing chemical equations requires consistent practice. Start with simpler reactions and gradually move to more complex ones, always remembering the law of conservation of mass. Many online tools and textbooks offer practice problems with solutions to help solidify your understanding. The ability to balance equations is not just an academic exercise. It's a critical skill for anyone working in chemistry, chemical engineering, or related fields. It underpins calculations for stoichiometry, reaction yields, and understanding industrial processes, ensuring safety and efficiency in real-world applications.
Summary. Well done. You have completed the course, Understanding and Balancing Chemical Equations. You should now be familiar with Introduction to Chemical Equations and Word Equations, Balancing Equations, Conservation of Mass, Counting Atoms and Balancing Simple Equations, State Symbols and Balancing Complex Equations. Practice and application. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.